Hello everyone, today we are introducing our course project, Optimizing Grocery Shopping, a time efficiency analysis of merge sort and quick sort algorithms for prioritizing shopping lists. Our group members are Yanqiong Ma, Zhiqian Zhang, and Rushan Liang. Next. Let's outline what we'll be covering in today's presentation. So we will introduce a project introduction and a quick sort implementation, merge sort implementation, and a conclusion. Imagine being a grocery store with limited time, facing the daunting task of sorting through a list of items. Today, we're not just discussing algorithms, we're addressing a real-world challenge. How can merge sort and quick sort algorithms make a tangible difference in the speed and the efficiency of grocery shopping compared to the traditional eye scanning method? Next. This is basically each member's motivation. Next.
Okay, so let's talk about the shopping list problem. So if you look at on the left side, you can see that we have 6 items. So if the items is only 6, you can easily icing off of the priority. So you can see that the first priority will be meat and the second priority will be bread. However, if you expand this shopping list to like 128, you cannot easily icing out the result of priority. So we have to use a faster algorithm. But let's only focus on the easy version so we can show you how to do a quick sort using the shopping list problem. Okay, so let's talk about the quick sort concepts first. So it's basically a divide and conquer strategy. So firstly, you have to select a pivot item, and then you have to partition the list into 2 sublists. And all the items that are less than the pivot have to go left, and then bigger than the pivot should go right. And then after that, you have to recursively sort the sublists. Okay, let's use the simple list to go over the quick sort. So we can see that we have 6 numbers here, 4, 2, 3, 6, 1, 5. So at the end, we have to sort them from the smaller items to the bigger items. That is 1, 2, 3. 1, 2, 3, 4, 5, 6. That is the result. And then let's look at how we can do that. So firstly, we have to select the middle item as a pivot, and then let's focus that we have the left pointers and left pointer and right pointer, and we also have the start pointer and the end pointer. So our focus should be let all the less like the items that are less than the pivot go left, and then all the bigger items go to the right. So let's to see whether there are any wrong position items. We already found it. That is 4. 4 should go to the right because that is bigger than 3. And then we have to find another one that is 1 because that is the number that are less than pivot. So it should go to the left. So we only need to swap them so they can both be the correct position. So now we have the 1, 2, 3, 6, 4, 5. After we do that, we can move the left pointer to the right and move the right pointer to the left. And then we can see that 2 is less than 3, so it's in the right position, and 6 is bigger than 3, so it's also in the right position, so we can move the left and right pointers to the middle. And then let's check on the start and end pointer. So we can group that into 2. So we can see that the first group is 1, 2, 3, and the second group is 3, 6, 4, 5. So we can see that we have one pivot that is 2, and another pivot that is 6, right? So we have to check whether there's any wrong position. So for the first group, we don't have any wrong position. So they are already sorted 1, 2, 3. So it's perfect. Let's go to another group. So another group is 3, 6, 4, 5. So the pivot is also the middle item, that is 6. So we can see that the 6 should be on the right because there is 5 which is less than the pivot, so we have to swap them. After the swapping, we got here. And then we have to do another swapping because 5 should be bigger than 4, so it should be the right side, right? So we have to do the swapping. After the swapping, we finally got the sorted items. So 1, 2, 3, 4, 5, 6. Okay, so that is basically what the quick sort will look like. Okay, let's go over the time complexity right now. So the best case, it will be the n log n because you can imagine that the pivot can split the array into nearly equal halves. So it can be n times log n. And the average case will be this as well. And then the worst case is when the pivot is really small or really large. So imagine that we have like 0, 1, 1, 1, 1, 1, 1, 1, and that will be the worst case. So at that time, the time complexity will be n squared. Okay, let's do the space complexity. So although quicksort is a in-place sorting, the space complexity is not really a 1 because we have to consider about the stack depths, right? So when we use stack, we have to consider the spaces it's used for the recursion. So for the best case, the space complexity should be O log n. It is when the pivot element divides the array into 2 halves. And the worst case will be ON, which is like the example I said before, is like 0, 1, 1, 1, 1, 1. That will give us the worst case ON. Okay, let's go on to merge sort.
Yeah. For this part, we will present how we can apply the merge sort algorithm to prioritize shopping lists. Now we explore how the algorithm works. We begin with an initial list, detailing items alongside their priority levels here. First, break down the list into smaller segments until each segment includes a single item. Second, we merge these segments back together, ensuring the subarray are ordered during the merge. In this process, the numbers next to each item representing their priority decide the order of sorting. The black part indicates the merge steps, while the red part presents the dividing steps. Finally, we achieve a list sorted by a priority. Next, please. Yeah. Next, we would explore the complexity. For complexity, it breaks down the process into a logarithmic series of steps, where the list is rapidly halved until each segment includes a single item, needing log n steps. And then it highlights the merge of these halves, which take a bigger ON time for each merge. So the overall time complexity is bigger N log N. And regarding space complexity, it mentions the recursive stack, which needs log n space and the additional array of size n, so need to be accounted for. Therefore, overall space complexity is bigger On. And next, please. And in the last part, we would consider how to optimize the algorithm. First, recursive calls increase the usage of the function call stack. So we can consider using loops instead of recursions. Second, more efficient data structure can be adopted, such as using linked list instead of array, so that insertion and deletion operations will be more efficient. Third, merge sort require additional space to store the array, so there can be optimized through in-place merge. Finally, we consider parallel processing on multiple processors. Multiple subarray can be sorted and merged at the same time, reducing all over sort time. Yeah. Next, please.
Let's analyze the advantages and disadvantages of merge sort and quicksort. While merge sort offers predictable performance and stability, it comes with the trade-off of requiring actual memory. So in our course project, understanding these trade-offs become very essential as we apply the algorithm to real-world scenarios. Quicksort is the in-place sorting. Average case performance and adaptability make it a valuable tool. However, we need to be mindful of its potential worst-case performance and instability. Next, please. So in conclusion, merge sort with its divide and conquer approach showcase a better worst case behavior than quicksort. This isn't just a theoretical, it's a practical example of a time and space trade-off. In our course project scenario, both quicksort and merge sort emerged as potential alternatives, demonstrating their efficiency compared to the straightforward traditional eye-scanning method. Next, please. Thank you so much for watching. Please let us know if you have any questions.